Hi everyone, what's up? Welcome back to my tutorial channel. Daniel's here and today I'm going to talk about duration of an investment. First of all, why do we have to study duration? As we know, the present value or the current value of an investment depends on the current interest rates. Therefore, it is important that a financial institution have mathematical tool to measure the impact of changes in interest rates on asset values. We are going to explore two tools, duration and convexity. Duration is a tool to estimate changes in present value due to a change in interest rates based on the first derivative of the function. And convexity is a tool to illustrate the curvature of the present value, the u function, and can be measured by the second derivative of the function. Remember, in calculus, when you investigate a function, the shape of the graph of the function can be told by the first derivative and the second derivative. The first derivative tells about the increasing and decreasing properties of a function, and the second derivative tells about convexity. So it's similar in financial investment. We are going to investigate the behavior of the present value when there is a small changes in interest rate using duration and convexity. So once we know how the present value and the current value of an investment change after a small change in interest rate, how can the institution protect itself from the effect of future changes in interest rates? That is a question about immunization. Immunization and convexity will be discussed in the next video. In this video, we are going to concentrate on only duration. Let's get started off with the simplest case, duration of a single cash flow. Here is an example. Let's consider two zero-coupon bonds, each with a maturity value of $1,000. The first bond matures in 10 years and the second one matures in 20 years. Both bonds are budgeted today to yield 6% effective. What are the prices of these two bonds at 6%? And suppose that the effective rate of interest suddenly increases by 0.1% to 6.1%. What would happen to these prices? So in this example, we are going to investigate the behavior of the price function when there is a small increase in interest rate. It's clearly that before an increase in interest rate, the price of the 10-year bond is 558.39 and the price of the second bond is 311.80. After the interest rate suddenly increases by 0.1%, the price of the 10 years bond is 553.15, dropped by $5.24. And the price of the 20 years bond is 305.98, dropped by $5.82. We see that after a small changes, 0.1% in interest rate, the price of the 10-year bond decreases by $5.24, which is negative 0.94% of the original price. And the second bond, the price of the second bond decreases by 5.82, which is negative 1.87% of the original price. So if you compare these two changes, you can see that negative 1.87% is almost double 0.94%. That means the second bond is more sensitive. So we see that because the term of the 20 years zero coupon bond is twice the term of the 10-year zero coupon bond, the price of the 20-year zero coupon bond is twice as sensitive to a small change in interest rate. And the price of sensitivity of a bond to a change in interest rate is just the percentage change in price to a change in interest rate. The duration is the time remaining to a single cash inflow or cash outflow. Macaulay duration. In the first example, it was easy to define duration in case of a single cash flow. It's simply the time remaining until the cash flow. For the 10-year zero coupon bond, the duration was 10 years, and for the 20-year zero coupon bond, the duration was 20 years. And we have seen that the greater the duration, the more sensitive the present value is to the changes of interest rates. Now we are going to consider an asset with multiple cash flows, such as a coupon bond or mortgage. Example 2. Consider a bond with 5% annual coupons maturing at $1,000 in 10 years. The cash inflows from the bond are the $50 coupons annually for 10 years and a $1,000 redemption value in 10 years. So to define the duration for a combination of multiple cash flows, it seems reasonable for duration to be defined as some kind of average of the duration of the individual cash flows. A simplistic approach would be to use the arithmetic average of the time of each cash flow weighted by the amount of cash flow. So the duration using such average is 8.5 years. However, we think about the duration might be calculated using waiting time of each cash flow by the present value instead of the amount of the cash flow. So the duration is 8.02 years. The second approach is called the Macaulay duration. In short, Macaulay duration can be regarded simply as the weighted average time of a series of cash flows, with each weight equal to the present value of cash flows. Macaulay duration can also be defined in terms of sensitivity of the present value of the cash flow to a change in interest rate. In this lesson, we consider two types of duration because when we learn about measurement of interest, remember there are two types of interest, the force of interest rate and the effective interest rate. So corresponding to these two interest rates, we have two duration. The Macaulay duration, or simply called duration, is calculated using the force of interest rate. So duration, Macaulay duration is just the first derivative of the present value function divided by the present value, and that is summation of t times v to the t cash flow times t over summation of vt times cash flow times t. We can understand Macaulay duration is basically negative the first derivative of the price over the price, where the differentiation is respect to the force of interest rate. And corresponding to the effective interest rate, we have the modified duration. The modified duration is notated as d mod, and it is computed as the first derivative of the price function respect to I over the price function. And there is a relation between the Macaulay duration and the modified duration. The modified duration is just v times the Macaulay duration. The modified duration can be understood basically as the negative of the first derivative of the price function respect to the effective interest rate I over the price function. and the differentiation here is respect to the effective interest rate. First order modified approximation. So we have learned how to define the modified duration. Now we are going to use the modified duration to estimate the change in the present value of the cash flows for a small change in the interest rate. And to do so, we set up some notation here. Let I naught be the initial interest rate at which the present value of the cash flows is determined, and I be the new interest rate that is very close to I naught. So by definition, the modified duration at the interest rate I naught is equal to negative the first derivative of the price function respect to interest rate I at the point I naught over the price at I naught. Using the definition of the first derivative, the first derivative of the price function respect to I is just the limit I approaches I naught of pi minus pi naught over I minus I naught. The whole thing here we divide by p of I naught with negative side to define the modified duration. So for this approximation, we are going to solve for pi. So pi is approximately p of I naught times 1 minus I naught times the modified duration at the interest rate I naught. And similar to the modified approximation, we have the first order Macaulay approximation using Macaulay duration. Similar, we set I naught delta naught to be the initial interest rate and initial force of interest rate, and I and delta are the new interest rate and force of interest rate. So using definition of Macaulay duration, we got d max at I naught is equal to d max at delta naught. This is equal to the negative first derivative of the price function over the price function at the point I naught. And by definition, d over this delta of p of I naught is equal to limit I approaches I naught of pi minus pi naught over delta minus delta naught. And remember, in the lesson of measurement of interest, the force of interest rate sigma and effective rate interest have a relation. Sigma is equal to natural of 1 plus I. So we replace delta as natural of 1 plus I and delta naught as natural of 1 plus I naught. So we are going to derive this approximation to solve for pi. So the Macaulay duration at I naught is approximately negative by I pi minus pi naught over natural of 1 plus I over 1 plus I naught times the price at I naught. And we multiply both sides with natural of 1 plus I over 1 plus I naught. We got d max I naught times natural of 1 plus I over 1 plus I naught is approximately p of I naught minus pi over p of I naught, and this is equal to 1 minus pi over pi naught. Next, we are going to use the property of exponent. Remember the power rule, r times natural of a is equal to natural of a to the r. So the left hand side right here is the same as 1 plus I over 1 plus I naught to the d max I naught. Natural of 1 plus I naught time over 1 plus I naught over to the d max of I naught. And we to get rid of natural, we take exponent both sides. So 1 plus I over 1 plus I naught to d max at I naught is approximately e to the 1 minus pi over p of I naught. And remember, an approximation for e to the x is 1 plus x. So e to the 1 minus pi over pi naught can be approximately by 1 plus pi over pi naught minus 1, which is equal to pi over pi naught. So we are going to take the reciprocal both sides and then solve for pi. So pi is pi naught times 1 plus I naught over 1 plus I to the d max of I naught. So this is how we approximate the price of an investment or cash flows at an interest rate near I naught. Duration of a portfolio. For the portfolio, the duration is the present value weighted average of the duration of the individual components of portfolio. So the Macaulay duration for the entire investment is the summation of pi times d max I over summation of pi. For example, there are 3 bonds in a portfolio of assets. The Macaulay duration of the entire portfolio is 10 years. The duration of the first bond is 8 years. The duration of the second bond is 6 years. The price of the first bond is twice the price of the second bond and half the price of the third bond. What is the duration of the third bond? So for this question, for convenience, we are going to let the prices of the 3 bonds are 2, 1, and 4 respectively. So using the formulas, we have the entire Macaulay duration is 2 times the Macaulay duration of the first bond plus 1 times the Macaulay duration of the second bond plus 4 times the Macaulay duration of the third bond over the sum of the price. So 10 is equal to 2 times 8 plus 1 times 6 plus 4 times Macaulay duration 3 over 2 plus 1 plus 4. So the Macaulay duration of the third bond is 12. So that was everything about duration. Now we are going to do some practice. The first question, find the Macaulay duration of a perpetuity due with level annual payments at an effective annual rate of interest of 3%. So just use the formulas. For this perpetuity with level annual payments, the Macaulay duration is summation of TV to the TAT over summation of V to the TAT. So in the front, at time 0, we have the cash inflow $1. So we got T is 0 and AT is 1. And this is V to the naught. Then for the time 2, we got T is 2. $1 is 80, and V is the present value of $1, and so on. And the denominator is just the present value of this perpetuity due. So the front, the numerator is basically an increase in perpetuity, and the denominator is just perpetuity due. So the Macaulay duration is 1 over ID, the whole thing divided by 1 over D, and simplified to be 1 over I. Using I as 3% interest, we got the Macaulay duration is 1 over 0.03, which is 33.33. Second question, consider a bond whose face amount is $1,000 that is purchased on January 1st, 2010 and matures on December 31st, 2020. The coupon rate is 8% annually and the effective interest rate is 8%. Coupons are back annually. Calculate the Macaulay duration on January 1st, 2018. Remember, the duration is the time remaining until the cash flows. So on January 1st, 2018, we have 3 more cash inflows. At the end of 2018, we got $80 coupon At the end of 2019, we have another $80 per bond, and at the end of 2020, we have 80 with 1,000 redemption value. So at the end of 2020, we got $1,080. So the Macaulay duration is 80 times 1 times V plus 80 times 2 times V squared plus 1080 times 3 times VQ over 80V plus 80V squared plus 1080 VQ. So the Macaulay duration for this investment is 2.783. Question 3. Consider a 14 years bond with 6% semi-annual coupons maturing at par and selling at par. Find the Macaulay duration of this bond. So for this investment, we have a bond with semi-annual coupons. So 6% semi-annual coupon, that means 3% for each half year is the coupon rate. And we are going to let F be 1 for convenience. So because this 14 years bond with 6% semi-annual coupon maturing at bar and also selling at bar. So 1 is equal to 0.03 A28 plus V to the 28. From here we have I is the same as R. So the interest is the same as the coupon rate, which is 3%. So the nominal interest rate is 6% compounded semi-annually. And we're going to use the interest rate to compute the Macaulay duration. Macaulay duration at the numerator, at time 1/2, we got 0.003. And at time 1, we got 0.03 until times 24. And also at time 24, we got the redemption value of the face amount $1. So the numerator is 0.03 times 1/2 V plus 0.03 V squared plus dot dot to 0.03 times 14 V to the 28 plus 14 V to the 28. And the present value of this investment is just 1 because we set F to be 1. And F is the face amount and also the price. So using 3% interest rate for each half years, we got the Macaulay duration is 9.66. Here, if we factor 0.03 and 1/2 out, we got from V to V28. V and then V squared to V28, we got an increase in annuity with the term of 28 coupon payments at 3%. So the duration in this investment is 9.66. Question 4. Find the Macaulay duration of a 14 years mortgage with level annual payments of $80 at an effective annual rate of interest of 3%. So this is a mortgage with level annual payments and no redemption value because this is a mortgage, not a bond. So the numerator is, we got 80 times 1 times V plus 80 times 2 times V squared. For each term, we basically just times with the time value. So at time 1, we multiply with 1. At time 2, we multiply with 2. At time 14, we multiply with 14. And then the denominator is the present value of this mortgage. Using 3% annual interest rate, we got 7.02 is the Macaulay duration. The TOF turns out to be an increase in annuity with 14 terms and interest rate is 3%. And the denominator is just the present value of annuity immediate of 14 years. Here 80 and 80 cancel out, that's why we don't have 80 at the second line. So 7.02 is the Macaulay duration. These two steps are just the basic formulas of annuity due and increasing annuity. Question 5. Calculate the Macaulay duration of an asset. Given the price PI is 81.31, the first derivative respect to I is negative 552.59, and the interest rate is 3%. So the Macaulay duration is 1 plus I times the modified duration. And remember, the modified duration is negative the first derivative respect to I over PI. So the Macaulay duration is 1.03 times 552.58 over 81.31, and the Macaulay duration is 7. Question 6. An asset provides two cash inflows, 230 in 2 years and 900 in 7 years. Given an effective annual interest rate of 3%, find the modified duration of the asset. So basically we just use the formulas. The modified duration is summation of AT T V to the T plus 1 over summation of AT V to the T. Remember, for the DMAX, the Macaulay duration, we have here V to the T, and for modified duration we have V to the T plus 1. That is the only difference. So 230 is at time 2, so AT is 230, 2 is T, and V to the T plus 1 here is V to V cube, and V is 1.03 to the negative 1, so V to the T plus 1 here is 1.03 to the negative 3, and similar for the second terms. The denominator is the present value of this cash inflows, and the modified duration in this case is 5.69 using interest rate 3%. Question 7. What is the modified duration of a 4-year bond with annual 10% coupons and a 10 years yield to maturity? So again, just apply the formulas. The modified duration is just summation of AT/T V to the T plus 1 over summation AT V to the T. Here V is 1.1 to the negative 1, which is 0.909. And here we have only 4 cash inflows, 0.1 at time 1, 0.2 at time 2, 0.3 at time 3, and 1.1 at times we got 0.1 at time 1, 0.1 at time 2, 0.1 at time 3, and 1.1 at time 4. So the modified duration is 3.17. Question 8. A portfolio consists of 3 bonds. Bond 1 with Macaulay duration of 19 years and a price of $81. Bond 2 with Macaulay duration of 9 years and a price of $92. Bond 3 with a Macaulay duration of D years and a price of $91. Find D given that the duration of the entire portfolio is 12. So just use the formulas. The entire Macaulay duration is 12. This is equal to summation of price time duration. For the first bond, the price is 81, the duration is 19. The second bond, the price is 92, duration is 9. The third bond, the price is 91, and the duration is unknown. The denominator is the total price, so it's 81 plus 92 plus 91. So we solve for D. So D here is 8.8. That means the duration of the Macaulay duration of the third bond is 8.8 years. So that is everything for today. Thank you so much for watching my video. I hope you guys enjoy my video, and I hope it's useful for you to practice for exam FM. Bye, and see you next time.